Hello, I'm Benjamin Miss. This is Introduction to Cognition, Sensation, Perception, and Attention. Sensation and Perception. Sensation and perception are terms often used together, but they refer to two parts of a global process. Sensation is what your senses detect, so perception starts with sensation. Perception is related to attention, as it describes whatever reaches the level of awareness. This section will consider some automatic processes involved in the way our minds process information and construct our experiences. Our perception is limited, and we do not perceive reality. Consider the story of Plato's cave, described by Plato in his Republic. Plato lived over 2,000 years ago and taught Aristotle, another famous philosopher. The main reason for the popularity of Plato is that Aristotle's student was Alexander the Great, who spread Athenian philosophy throughout the Mediterranean world. In the cave, prisoners have been shackled their entire lives facing the wall of the cave. Behind them is a walkway and a fire. People on the walkway hold things that cast shadows on the wall. The idea is that, for these prisoners, the shadows on the wall are their reality. Plato describes a situation where a prisoner is unshackled and taken up to the surface. At first, everything would seem unreal, but the prisoner would eventually acclimate. If the prisoner was returned to the cave and tried to tell the other prisoners what they saw, the other prisoners would not believe them. According to Plato, this story argued that philosophers were the only ones who understood truth, but they are not believed when they try to explain those truths to the people. Actually, the allegory of the cave is a great example of human perception. The reality we perceive is related to what we have the ability to perceive. We know that dogs have a larger range of hearing and smell. Dogs might start barking because they hear a high pitch or smell another dog nearby. Many birds have a larger range of vision and color, sensitive to the ultraviolet spectrum. Some snakes can sense infrared heat with a specific organ, allowing them to find prey in the dark. Some sharks and birds are sensitive to magnetic fields. This allows sharks to estimate the size of their prey in murky water, and it assists birds with migration. It is obvious that what we perceive is only a fraction of what is possible. We are the prisoners in the cave. We know that even if we were brought out of the cave into the sunlight, we would still only perceive what our senses allow us to. The cognitive scientist and philosopher Donald Hoffman argues that we did not evolve to perceive truth, but rather to perceive only what is necessary for our survival and reproduction. He demonstrates that the biological costs associated with perception limit what a species will perceive, and that those species that perceive things not needed for their own survival and reproduction will become extinct. They will be outcompeted by species better suited to the tasks of survival and reproduction. Psychophysics. Early psychology was focused on an attempt to study the characteristics of the mind and ended up laying groundwork in psychophysics. Psychophysics examines the relationship between physical stimuli and mental processes. It can be as simple as showing people similar stimuli and asking people to make judgments about those stimuli. Two early pioneers, Ernst Weber and Gustav Fechner, began to demonstrate that it was possible to link sensation and perception, and develop laws for those things. Weber showed that each of our senses differs in sensitivity. Weber's law allows for the careful calculation of how much change is necessary for us to perceive differences in the intensity of a stimulus. Fechner noticed that this change detection was not constant, and that at very weak and very strong intensities, our perceptual abilities no longer followed Weber's law and devised another formula showing that perception is not linear but logarithmic. This means that you need a greater change in intense stimuli to notice a difference, but for weak stimuli, you will notice a smaller change. For instance, if music is playing quietly, you may notice a slight increase in volume, but if music is at club levels of loudness, you would likely not notice if the volume was increased slightly. Weber also explored two-point discrimination using a tool like a compass used for drawing circles. He showed that our ability to detect the difference between 1 and 2 points of touch varied depending on where on the body we were touched. Fechner was the first to suggest that cutting the corpus callosum might lead to each hemisphere having its own consciousness. And he also studied grapheme color synesthetes, which are people with a form of synesthesia where letters appear to be different colors to different viewers, though each letter is always perceived as the same color. A synesthete might perceive every A as blue, every B as pink, etc. There are various forms of synesthesia, and we now believe synesthesia is caused by connections between brain areas that are not typically directly linked. Two other pioneers in the late 1800s, Wilhelm Wundt and Hermann Ebbinghaus, explored different characteristics of the mind, demonstrating that something as mysterious as mind could be investigated. Wundt was a student of Hermann von Helmholtz, the widely respected researcher who demonstrated that humans had 3 types of color sensors in their eyes. Wundt created a simple machine in order to test attention switching. It was believed that it took no time to switch attention from one thing to another. Wundt showed a pendulum moving against markers, and when he played a sound, he asked people to report the position of the pendulum. Since he could carefully measure the exact position of the pendulum when he played the sounds, he could see that it took time for his subjects to process the sound and report the position of the pendulum. This was the first instance of demonstrating that mental processes take time. Wundt also developed his theory of structuralism, which attempted to study the inner workings of perception by finding the elements of perception. His analogy was that our perceptions were like molecules, made up of various concentrations of elements in the same way chemical molecules work. This method did not work, but given the scientific thinking of the time, it wasn't a bad idea. Wundt's conflict with William James has been replayed with various scientists throughout history. James accuses Wundt of getting lost in the details, while Wundt accused James of being a philosopher rather than a scientist. Somehow, we must balance our focus on the details with keeping track of the big picture. Sometimes conflict is also due to personalities. There is some evidence that early in his career, James attempted to work with Wundt, but was unable to connect with him. Hermann Ebbinghaus developed a model for memory by creating lists of nonsense words and trying to memorize those words. Without modern technology, he developed the forgetting curve, precisely calculating the decay rate of information. In fact, nearly 150 years ago, Ebbinghaus demonstrated that cramming is bad for learning. He showed that spreading out practice into multiple sessions was the best way to commit information to memory. And yet, 150 years later, many students still study inefficiently. We can absolutely use research on the mind to improve our lives. Modern psychophysics explores many other areas, including our ability to perceive faces in fields of dots or under various stages of degradation, our ability to tell the difference between biological and mechanical movement, Some researchers look at how our visual system adapts under various conditions, or how well we perceive slight changes. We can measure memory, reaction time, and speed of processing. The subfield of human factors is interested in the direct application of studies of sensation and perception. Though the field includes ergonomics, The psychological side of human factors works with making things easier to use. From something as mundane as the ideal placement of elevator buttons, applications include flight and space travel. For example, virtual reality, VR, requires a massive amount of computer processing to maintain the various illusions. Since we can only focus on pieces of reality, studying perception can allow for a reduction in VR rendering, which leads to faster processing and a more seamless experience. In some ways, the study of sensation and perception requires as much engineering knowledge as experimental psychology knowledge. Signal detection theory. Signal detection theory came out of World War II observations regarding radar. Radar allowed for an early warning of incoming bombers, allowing time for defensive planes to intercept them and civilians to get to shelter. However, early radar was not very accurate. It could be difficult to tell the difference between an enemy bomber and a flock of birds. There was static and interference and random noise, so the radar operator had to figure out whether to sound the alarm. If they always sounded the alarm, then people would be worn out, running to shelters all the time, and planes would take off for nothing. If they rarely sounded the alarm, then bombers would fly over and drop their bombs and wipe out airfields and civilians. The radar operators in this case had to develop a threshold for when they would sound the alarm. This meant they wanted to minimize the false alarms, but also minimize the times they failed to sound the alarm. It is better to have more false alarms than misses, but as noted previously, too many false alarms was also a problem. The table here shows the possible responses to various stimuli. How people set their threshold when confronted by ambiguity became an interesting area of study. This is called a sensitivity index, or D', and operators with the best sensitivity index would be the most successful. With experience, we adapt our sensitivity index for a given type of stimuli, and we can adapt our sensitivity index to all sorts of events. The table is particularly interesting because it is related to general experimental design. In an experiment where you compare groups A and B, there is always a chance that the true state of the world is no difference between A and B, and you say there is a difference, which would be a false alarm. There is also the possibility that there is a difference between A and B, and you say there is no difference, which would be a miss. A well-designed experiment will minimize the chances of misses and false alarms. In experimental design, a false alarm is called a type 1 error, and a miss is called a type 2 error. But as with all aspects of human perception, we account for the probability that we might be wrong. Sensation and perception are not absolute. If your sensory receptors cannot detect something, it cannot possibly be perceived. Even if it is detected, it might not be perceived. The absolute threshold is defined as when a stimulus or change can be detected at least half of the time. If you've ever had a hearing test in a sound booth, they are measuring whether the intensity of the sound is high enough for you to hear it. Weber's just noticeable difference is when you are aware of a change. How much brighter does something have to be for you to notice? How much louder does something have to be before you notice? For most of our perceptual abilities, it takes quite a bit of objective difference before we notice it. The term psychometrics encompasses the range of human psychological testing that includes knowledge, abilities, and personalities. Psychometrics is also used to measure subjective changes to physiological stimuli such as brightness, volume, and weight. These lead to a psychometric function. A psychometric function is a graph of the relationship between stimulus strength and perception. Consider a hearing test. Once you reach 50% performance, you are at the just noticeable difference, where anything at a lower volume is not perceivable. As the volume increases, your performance increases until the volume is so loud you are performing at 100%. These experiments allow us to investigate individual performance in order to diagnose sensory problems such as hearing and vision loss, but also to understand the general range of human performance. Our knowledge of human sensation and perception often comes from these types of experiments. Illusions and perception. Illusions allow us to understand that we are seeing something that is not real. Consider the difference between medieval and Renaissance paintings. Perspective seems strange. What is large and what is small seems more about importance to the painter rather than what we would typically see visually. Paintings like this can appear jumbled. We lack perspective. In some cases of devotional art where the motif was mother and child, one might wonder if the painter had ever actually seen a baby. Things were symbolic, not meant to mimic visual reality. It wasn't until the Renaissance that European art began to use visual cues in order to approach realism. Consider the second image, where the figures in the foreground now appear larger, creating the illusion of depth. There are two broad classes of cues our visual systems use to rebuild the world, which are binocular cues, which rely on the disparity between what our eyes see, and monocular cues, which are only needed to process information in one eye. Art generally uses monocular cues to give us the illusion that we are viewing a three-dimensional scene. One of the reasons that medieval paintings appear cluttered and strange is that our visual systems are attempting to use the same cues we would use in the real world, but the artists are not taking advantage of those cues. Interposition is when one object is in front of another. In a painting, this means that one item will appear to be behind or further away than the one in front of it. The man on the left of the image is in the front of a group of behind him, so he does appear closer. Aerial perspective is how objects that are farther away appear less clear. In the first painting, the people who are meant to be farther away appear just as clear as the people who are closer, making them seem small and near, rather than of typical size and far. Linear perspective is how objects that are far away appear smaller than objects that are close. Illusions take advantage of various aspects of our visual system in order to illustrate ways we can be fooled by perceptual cues. The study of illusions can tell us a lot about this. In the same way, artists introduce realism in paintings. We look for the same cues we use in photographs to get an idea of perspective. Consider the Ponzo illusion, which looks like this. Which line is longer, the one on top or the one on the bottom? We know if you hold two pencils up to that image and place them at the edges of the two horizontal lines, you can see the pencils are parallel. You know the horizontal lines are the same length. Yet when you remove those pencils, the lines no longer look the same length, even though you know they are. This is like the Wile E. Coyote illusion, when he paints on a rock wall what looks like a road. We know from looking at the world that if you look into the distance, lines appear to converge. A road looks narrower further away than it does up close. The same illusion works in art. This is exactly the linear perspective mentioned earlier, where a road appears to narrow in the distance. Now for a really baffling one, the checker shadow illusion. This illusion takes advantage of our use of shadow and light in perceiving color. Are the spaces marked by A and B the same shade? They look different to me. B is clearly much lighter than A. But when we draw a connection between them, as we see in the next image, they appear to be the same color. If we were to take this image and remove everything except squares A and B, you can see that the two squares are the same shade. I didn't believe this myself. Go ahead and get a copy of the first image and cut out the squares marked A and B and place them next to each other. It becomes been fooled. We are using relative information. Our knowledge of shadow, for instance, tells us that if a shadow is cast, the underlying area will appear darker than it is, so our mind lightens it. We know what checkerboards are supposed to look like, with alternating dark and light spaces. These pieces of information are analyzed by an automatic process that uses comparison in order to calculate the various shades on the checkerboard. Top-down processing is when we use information from our experience in order to predict and order perceptual information. Bottom-up processing is when we use only environmental information. Usually, these processes work together. Often, we see the term perception being used to generally describe bottom-up processes and apperception being used to describe top-down processes. Illusions are often influenced by apperception or our expectations about the world. We use visual cues to interpret distance, and these cues are used by artists to give the impression of distance and perspective. Check out the hollow mask illusion. You can find it by searching on popular video sharing sites. What you will see is a rotating convex mask on a pedestal. Most people never see the inside of the mask because our brains adapt to it, so it always looks like the outside of the mask. The mask turns halfway, and the inside pops out at us, looking like the front of the mask again. Schizophrenic patients, however, are not fooled by this illusion. This suggests that they may not be accessing top-down information as we would expect them to. A typical brain predicts the experience based on visual cues. One of the oldest visual illusions is the Necker cube, or 3D cube. First published by Louis Necker in 1832, the cube shows us that human perception is flexible. Which is the front of the cube, the lower left or the upper right? Without any other visual information, you should be able to see it both ways. While we are sensing the exact same stimuli, our perception is changing between two different possible images. The next image, the Ebbinghaus illusion, was designed by Hermann Ebbinghaus in the late 19th century. It shows two orange circles of the exact same size, surrounded by different-sized blue-gray circles. The orange circle on the right looks larger than the orange circle on the left. It doesn't matter that you know this is an illusion. You cannot see the orange circles as the same size. You might even be measuring them right now to confirm this. Go ahead, you're not alone. It can be jarring to see how much our perceptual systems rely on that top-down processing. This example shows us how we use cues from the surrounding objects to calculate the size of the objects inside. Do you remember the 2015 debate about whether the dress was blue and black or white and gold? Personally, I never understood it because the dress looks light blue and gold to me. It doesn't matter what the color actually is. We are looking at a reduced quality image. That creates ambiguity. When there is ambiguity, we characterize things into one category or another, and that is how we then perceive it. It is difficult to go back and perceive things differently than we've already decided. Remember the Yanni Laurel sound clip from 2018? That one is extremely similar in principle. Those two-syllable words at first appear very different. Yet, when we consider the characteristics of those sounds, we understand the Y and L are similar, as are the N and R. There are a number of reasons for the difference in perception, one major one being that as we age, our ability to perceive sounds changes. We no longer are sensitive to the high-frequency sounds. There is variability here. For those who listen to very loud music can lose those high frequencies earlier than those who protect their hearing. There are also health and genetic factors. Younger people tend to hear Yanni. This tells us there is ambiguity, and the auditory acuity of the listener, or what parts of the sound they attend to, will influence perception. For those of you unfamiliar with the way we produce sounds, here are the audio waveform and audio spectrogram views of me saying Yanni, Laurel, button, and pencil. I made these recordings and images using Audacity, an amazing piece of free software. You can see the differences in the characteristics of the sounds, but Yanni and Laurel look quite similar, especially compared to the other two words. We know the speaker on the recording sounds somewhere in between my version of Yanni and Laurel, which means that, like the white or blue dress, we are forced into categorizing ambiguous stimuli. The McGurk effect is a fascinating auditory illusion, where a speaker's mouth does not match what we hear, and so we change what we hear to match the visual scene. It is better to view an example of this, and you can find many videos of the McGurk effect. A sound file will continually play the sound ba, but the speaker's mouth will sometimes appear to say ba, and sometimes appear to say fa. Say both of these sounds out loud and pay attention to what your mouth is doing. Now, when you watch the video, you know that the sound is only ba, because if you close your eyes, that's all you hear. But if you watch the speaker's mouth say fa, you hear fa instead of ba. This means you are using visual information to change what you perceived auditorily. Not only that, but it means you are changing what you hear after the fact, because auditory information is processed up to 100 milliseconds faster than visual information, which means when you watch the speaker's mouth say fa, your brain processes ba, holds onto that information, compares it with the visual stimulus, and then changes what you heard. The story of illusions is useful because it allows us to understand how our brains sense, perceive, and reconstruct reality. We really do experience the world incorrectly, though that is related to the energy cost of perceiving the world perfectly. The cognitive scientist Donald Hoffman demonstrates that true perception of reality, what he calls veridical perception, is contrary to evolutionary fitness. An organism needs to perceive the minimal amount of information to survive and reproduce, and that the cost of perceiving truth is higher than the benefit. To Hoffman, our perception of reality is akin to the operating system on your computer. Your folder files are representations of the ones and zeros of machine language, useful for moving files around, but not reality. He argues that even what we think of as a neuron is simply the best representation we can make, real to us, but perhaps not a good representation of the underlying reality. Attention. Early, it was noted that perception starts with sensation, but also relies on attention. We have multiple attentional systems that work in concert to process various types of information. Recall that the use of the word attention when we are often referring to basic consciousness, rather than what we mean by consciousness. Here, we really are focused on attention and processing related to that. Focused attention refers to our ability to respond to stimuli, and vigilance refers to our ability to sustain attention for a significant length of time. Selective attention is your ability to ignore distraction, such as when you ignore what other students are doing in class in order to focus on the lecture. The influential attention researcher, Michael Posner, studied both overt attention and covert attention in his Posner cueing task. Overt attention involves eye movement to focus on a stimulus. Covert attention involves more of a general awareness of a stimulus, but without direct focus. Covert attention allows us to shift attention to part of the visual field, while still keeping our eyes focused on the center of the visual field. For instance, Posner would show two boxes around a central fixation point, like the image you see here. A target would appear in one of the boxes, and the participant would have to respond as quickly as possible to the position of the target. Posner studied covert attention by giving cues that were correct most of the time, such as an arrow that would point left or right before the target appeared. Most of the time, the target would be in the same place the arrow pointed, but not always. In order to maximize reaction time, covert attention would shift to the indicated box, but the participant would have to maintain a general awareness of the whole visual space. This task has been used to study the extent of brain injury and neurological disease. Are you good at multitasking? The answer is no. If you think you're good at multitasking, you'll likely have some skill at alternating attention or switching back and forth between tasks. Can you talk to a friend on the phone while watching videos and listening to what they say? Yes, but both tasks suffer. You miss things in the video, and you miss things your friend says. The dichotic listening task involves two different streams of information, one presented to each ear. We can combine similar information from two different streams, and depending on the complexity of the information, we may completely miss information from the unattended auditory stream. Tasks like this tell us that we have a limited pool of attention, and when we use divided attention, we are splitting the pool across different tasks. Studies of attention show us that dividing our attention through tasks like texting while driving can be horribly dangerous. Attention is automatic, meaning that rather than deciding to focus on things, stimuli often draw our attention. Similar to James's transitive thought and Kahneman's System 1, things in the world draw our attention rather than through our choice to focus on those things. The philosopher Daniel Dennett describes the attentional spotlight that can move from task to task without conscious control. Did you just hear a loud noise? You're already paying attention to it and trying to figure out what it was before you're even aware you heard the noise. What are you thinking about right now? Are you focusing the spotlight on this page? Or is your mind wandering? Sometimes, if you find yourself reading the same paragraph over and over, it's time to take a break and come back refocused. Consider how processing is related to attention, particularly serial processing and parallel processing. We are able to filter out information by choosing what we attend to, but our filters are reliant on what we perceive. Consider these three arrays and find how many P's are in the series of R's, how many F's are in the series of P's, and how many R's are in the series of F's. It should take you longer to find the P's in the fields of R's, though it should also be difficult to find the F's in the series of P's. The R's, however, should be obvious. This perceptual pop-out happens in parallel processing when we can effectively analyze an array all at once. This relates to our ability to pay attention to various features. Since P has the same features as R, we have to look at every R one at a time in serial processing. Since R contains features F does not, the R's pop out at us, and we can effectively see them all at once. This type of task has additional applications in regards to the attentional spotlight. We seem to process angry faces in parallel and happy faces in serial, which suggests we have a bias towards angry faces. This makes sense because angry faces indicate danger, and dangerous things draw our attention. The cognitive processes involved in sensation, perception, and attention help us to understand a great deal about the mind. It is easy to take these built-in cognitive processes for granted, but our attraction to illusions tells us that we are aware of these complex processes even if we don't understand how they work. I hope you've enjoyed the discussion today about sensation, perception, and attention. Thank you, and I look forward to future discussions.